looking at a young black king.
Astro project, blast of a tech, pass your neck with the shit to leave a rapper erects from the back of a black Acura. Bullet ricocheted in its weight and it passed through your pecs. The assassin wet. All y'all know y'all don't have to go. Sawed off shoddy, make you potty, probably call the law. Me no gangster, I'm no tough, got me child of the most high. I get on the mic and you go, bye-bye. Devil don't test me, I throw shrapnel where your chest be. Shooting our family down in the streets, fuck the police, they ain't marching for me. Pull up, not that Rari, I ain't bad yet. I pull up, out that 85% of mass at. I put this on God, bad black is so hard. Bitch, I'm going back to Harlem in my West African garb.
Copyright disclaimer under Section 107 of the Copyright Act of 1976. Allowance is made for fair use for purposes such as criticism, comment, news reporting, teaching, scholarship, and research. Fair use is a use permitted by copyright statute that might otherwise be infringing. Man, peace to everybody, man, out there tuned into the Monster Warrior Clan YouTube channel. And those of you who will catch the replay, please like the show, share the show, tell a friend, I'm not going to be long. We're going to be very brief. Going to get into something real quick, and we're going to knock out like 15 minutes of your time, and then I'm going to let y'all get back to it. So again, I'm going to show the copyright disclaimer again. And from there, we're going to cook. Please like the show, share the show, tell a friend, we live.
Hey, it's Professor Dave. Let's check out the night sky.
He knows a lot about the science stuff. Professor Dave explains.
It's taken almost 10 billion years, but we've finally made it. We started with the Big Bang. We watched atoms form. We saw these collect to form stars and galaxies. We saw those stars explode to disperse the materials that would become all the planets. And we watched our own solar system form, including the planet Earth. Thus begins a new chapter of the story. Upon this Earth, biomolecules arose, polymerized, and became contained in cell membranes. Life was born, which slowly evolved and eventually brought about human beings like you and me. This fascinating chapter of the story is told by the fields of general chemistry, organic chemistry, biochemistry, and biology. Check out my tutorials on those subjects if you want to know more about that whole show, since it's more than a little involved, as one might imagine. But otherwise, to get back to astronomy, once human beings were thinking and talking and forming civilizations, they started to look up at the sky and wonder together about all the things we've been talking about so far. Stars, planets, and the penetratingly deep, dark cosmos. What did they think about all this? How did they begin to figure out all of these things? Let's take a moment now to see what they saw and try to make sense of their thoughts.
What is going on?
Early civilizations saw a night sky that was virtually the same as the one we see today, or at least the one we can see from a rural location, far away from all the smog and light pollution found in a large city. Objects have shifted their positions slightly, but apart from that, our ancestors saw thousands of stars that seemed to be fixed on some celestial dome or sphere, slowly rotating around us. They kept track of their positions by inventing constellations, or shapes that can be traced by connecting the dots. They require quite a bit of imagination to see, but our ancestors were creative and probably quite bored, so they projected a little bit of themselves onto the stars. They also saw other objects, most notably the sun and the moon, as well as 5 planets, all of which moved according to their own patterns, unrelated to the stars. The planets were named...
Time out. They could see 5 planets? I'm being sarcastic.
...named for gods, and their Roman names are the ones we still use today. For a long time, we believed that the Earth was the center of the universe, with the mysterious heavens swirling around us. While this notion seems utterly ancient to us now, it was the only conclusion we could have made in absence of any scientific knowledge. The planets moved along a particular line through the sky, but a bit more slowly than the stars, and the constellations they crossed in doing so were viewed as special. These were the constellations that came to comprise the zodiac, which are still the focus of astrology today, a relic of mysticism from times past. But some of what we learned in those times remains valuable today. We began to understand the cycles in the sky, and we used them to understand time, the seasons, and other phenomena. The most obvious unit of time that mankind has understood since prehistory is the day. The sun rises and the sun sets. This is the most noticeable cycle to any Earth dweller. But other cycles were visible too. The moon goes through phases in a predictable way, and this became the basis for the month. Over longer periods of time, we noticed seasons, or regular periods of warmer and colder weather. This became the basis for the year. These are all units of time that mean nothing whatsoever elsewhere in the universe, but on the Earth, they mean everything. They punctuate our human experience. Now let's discuss some more subtle observations we made over many generations. First, the stars rise and set just like the sun and the moon, and they do so resembling one huge sphere, with their distances from one another fixed. But after looking long enough, we realized that there is one point that doesn't move at all. In the northern hemisphere, this is called the North Celestial Pole, and the southern hemisphere has its South Celestial Pole. These coincide with the north and south pole of the Earth, and the reason for this is fairly intuitive in a modern context. The star directly above the axis of rotation for the Earth will appear not to move, because the North Pole is a point that experiences no lateral motion as the Earth rotates. This star, the North Star, was useful for navigation for thousands of years and remains useful to this day, leading any navigator in a northward direction, no matter where you're standing in the Northern Hemisphere. But for reasons that we now know have to do with Earth's motion around the sun, the celestial sphere changes very slowly throughout the year. Different stars are visible at different times of the year, as well as different constellations, and this was an important method of marking the passage of time. Rather than any meaningful message from the gods, this phenomenon occurs simply because we can't see stars behind the sun, because it's way too bright, and at different times in Earth's orbit around the sun is blocking different stars. We can only see stars during nighttime, when the half of the Earth we are on is pointed away from the sun. So some constellations go missing and others appear until we get back to where we started, all in a predictable annual cycle. The line that the sun traces in its movement across the sky is called the ecliptic, named as such because if the moon crosses this line, we have the potential to see an eclipse. We now understand that this line, followed by the planets as well, is simply the plane of the solar system. But the sun's path changes depending on the time of year, in a way that correlates with the seasons. So what are seasons, and why do we have them? Many people think that this has to do with the Earth's distance from the sun. Farther away, colder, winter. Closer, hotter, summer. But summer in the northern hemisphere happens at the same time as winter in the south, and vice versa, so that can't be right at all. Instead, the seasons occur because of the tilt in Earth's rotational axis. This is the imaginary line that the Earth spins around. As it turns out, this axis is not perpendicular to the plane of the solar system. It's actually 23.5 degrees from the vertical. This means that one hemisphere is getting more direct sunlight than the other at certain times of the year. In the summer, the axis of rotation is tilted towards the sun, and the northern hemisphere gets the most direct sunlight, while the southern hemisphere gets sunlight at an oblique angle. So the northern hemisphere gets more heat and more daytime. In the winter, the axis of rotation is tilted away from the sun, and the southern hemisphere gets lots more sunlight, more heat and more daytime, while nights get longer and colder up north. This tilt also explains the varying angle of the ecliptic. Because of the way the Earth is tilted during different times in orbit, the sun will rise and set at different places in the horizon. The spring equinox, or vernal equinox, as well as the fall, or autumnal equinox, are the 2 days where the sun crosses the celestial equator. The summer solstice and winter solstice are the days where the sun is the furthest away from the celestial equator, rising and setting furthest north or south. These days mark the passage of the 4 seasons, and we were able to observe this in the sky long before we knew why it happened. Ancient monuments like Stonehenge in England are very clearly structures based around these phenomena, as in this case, the openings between stone pillars are meant to frame the sunrise and sunset for an observer standing at the center, specifically on these special days. Other monuments, like pyramids and temples, exhibit some kind of alignment with the sun on certain special days as well. But contrary to whimsical conjecture, it is not necessary to evoke aliens or magic to explain this. It is just the result of careful observations of the celestial sphere over many generations. Lastly, the ancients were fascinated by the moon, as it is the only object that significantly changes its appearance over time. The moon has cycles in which it waxes and wanes, from full to new to full again, with crescent shapes in between. These are called the lunar phases. Their explanation is quite straightforward, and contrary to popular belief, it has nothing to do with shadows. Only the face of the moon that is pointed towards the sun is illuminated, and therefore visible. If that side is pointed towards Earth, when the moon is opposite the sun, the moon is full. If pointed away, when the moon is on the same side as the sun, it's new. Anywhere in between, and we get a crescent of some kind. If the moon passes directly between the sun and the Earth, that is called a solar eclipse, and the moon will completely block out the sun, leaving the Earth in its shadow. When the Earth is directly between the sun and the moon, leaving the moon in Earth's shadow, that is called a lunar eclipse. These were mysterious sights in the ancient skies, often interpreted as ominous signals from the gods. But just as with everything else, we began to learn how to predict these events as well. Let's continue and see what happened next in our quest to understand the cosmos. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me.
What does it mean to be a featherless?
It's Professor Dave. Let's take some measurements.
He knows a lot about the science stuff. Professor Dave explains.
We just talked about a few of the observations of the night sky that must have happened in every civilization throughout the world at the dawn of human history. But science is much more than just observation. It is about what we do with these observations. We look for explanations. We make models and predictions. We take measurements and see how they hold up to our predictions. If they don't match, we revise the model and try again. After many centuries of pure observation, our approach to astronomy became more mathematical. Some of the earliest known scientific calculations happened during the classical period of astronomy in ancient Greece and other contemporaneous civilizations. What were some of these calculations, and what did they tell us? First came the realization that the Earth is round. This idea first cropped up around the time of Pythagoras, although at that time it was not really based on logic, but rather on the aesthetic beauty and perfection of the sphere. So it wasn't very scientific. But just a bit later, with Aristotle, a more logical approach arose. He noticed that during a lunar eclipse, the shadow cast on the moon by the Earth has a curved edge. This is representative of Earth's spherical shape. It was also realized that the stars that are visible in the night sky depended entirely on one's location in the world. Moving north to south, a completely new set of stars becomes visible, and all the familiar ones vanish from sight. This is easily explained with a round Earth, as the other half of space that surrounds the Earth is only visible to the other half of the Earth. Once it was determined that the Earth is spherical, the next logical step was to attempt to measure the dimensions of the sphere. Eratosthenes was the first to do this, and with impressive accuracy. He reasoned that when the sun is directly overhead one object, it must cast a shadow on some other object sufficiently far away. He used a well in one part of Egypt and an obelisk in another part of Egypt to take some measurements. At noon on the summer solstice, the sun shone directly down the well, illuminating the very bottom. Simultaneously, the sun cast a shadow on the obelisk in Alexandria, revealing that the sun was 7 degrees off the vertical. Now let's draw a line from the bottom of the well to the center of the Earth, and another one back up to the base of the obelisk. By simple geometry, we can see that the angle of this sector is 7 degrees, which means that this distance represents a little less than a 50th of the way around the world. The distance between these locations was known to be 5,000 stadia, so we can use a simple ratio to deduce that the circumference is around 250,000 stadia, which is around 25,000 miles. Given that in ancient times, the only tool available was the naked eye, these are all demonstrations that you can reproduce yourself in case you're curious to try. Now that we are all set with the Earth, what about the distances to other objects in the sky? And how big are those? Incredibly, we were able to deduce some of these quantities as well. Take the moon, for example. Around the time of Eratosthenes, another Greek named Aristarchus did some similar work. He looked at the shadow of the Earth on the moon during a lunar eclipse, and by comparing the curvature of the shadow and the moon itself, he deduced that the moon must have a diameter around 1/3 that of Earth. He also made estimates regarding the relative distances to the moon and sun, and although those were not as correct as his other work, he was the first to suggest that the sun is much larger than the Earth, and even proposed that the Earth goes around the sun. There was not sufficient evidence for this idea at the time, so the geocentric model with the rotating celestial sphere reigned supreme for many more centuries. Eventually, we did correct this oversight, and as this was one of the defining paradigm shifts in the history of astronomy, let's move forward and talk about that next. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content.
Man, my finger tripping. Hold on, I'm trying to take that mute button off, but that mug ain't let me take it off. Now peep this. Just peep this.
When we left off with Aristarchus, he had correctly proposed that the sun is the center of the solar system rather than the Earth. But he was way ahead of his time, and the geocentric model remained in place for centuries. This model was perfected by Ptolemy in 2nd century Egypt. He improved on pre-existing models by finding a way to explain elusive phenomena like the retrograde motion of the planets. This was when a planet would seem to turn around and go back the other way in the sky for a few days before resuming normal motion. Now we understand very well that this happens because the Earth is passing the planet in its orbit and will thus appear to move backwards. But back then, with the geocentric model, it needed some serious explaining. He proposed that planets move on epicycles, which are smaller circles that themselves move around the larger circle that is the planet's orbit. And this model was able to predict the motion of the planets with reasonable accuracy. But it wasn't perfect, so it was tinkered with, making things more complicated, requiring a different formula for each planet. This went on for centuries until the 1500s, when it just no longer made sense. It was at this point that a paradigm shift in astronomy was necessary. The first to suggest a heliocentric model since the time of Aristarchus was a Polish man named Copernicus. He demonstrated with great precision that all of the problems with the geocentric model instantly vanished if the sun is placed at the center of the solar system. Objects closer to the sun orbit faster, and the retrograde motion of a planet like Mars is now simply the result of Earth overtaking Mars at a particular time in their respective orbits. As we pass by Mars with a greater angular velocity, there is a moment where it appears to move backwards, just like when you pass a car on the highway and it appears to you to be moving backwards, given its slower velocity. Copernicus even estimated the distances from the sun to each planet with great precision, using some ingenious geometric calculations. But there were still some issues to iron out. Critics of the heliocentric model had one very valid point. If the Earth goes around the sun, the apparent position of the stars should shift. It would be several hundred years before we had telescopes powerful enough to see it, but this shift does indeed occur. It is just incredibly small because of the staggering distances to the stars. We use this slight shift today to measure the distance to certain objects in space. To understand why this works, hold a finger in front of your eyes. Then alternately open and close one eye at a time. Your finger will shift left and right depending on which eye is looking at it, because your line of sight is originating from a different location. Keep doing this as you move your finger away from your face. The shift in location becomes less pronounced with greater distance. If you try this with an object across the room, it already starts to be relatively negligible. Now imagine that the Earth being on one side of the sun is your right eye, and the Earth being on the other side of the sun is your left eye. A distant star will change its position in the sky, just like your finger, but the star is so far away that we need mechanically precise machines to measure the apparent shift. But we do have these machines in the form of modern telescopes, and because we know the distance from the Earth to the sun, which is 1 astronomical unit, or about 150 million kilometers, if we then measure this apparent shift, we can cut it in half to get what we call the Stars Parallax. Then we make a right triangle with the Earth, the sun, and the star, and simply use trigonometry to find the distance to that star. If you need to, check out my trigonometry tutorials for loads of information regarding triangles and angles. Parallax, among many other phenomena, strongly corroborates the heliocentric model, such that there has been no doubt in its validity in the past few hundred years. The Copernican revolution had a tremendous impact on human culture. The notion that the Earth goes around the sun rather than the other way around is a fairly innocent claim to a scientist. One model fits the data much better than the other, and that's all there is to it. But the philosophical ramifications of this shift cut very deep. If the Earth goes around the sun, the Earth is not the center of the universe. Other astronomers, like Giordano Bruno, reasoned that if the sun is the center of this system of planets, and all the countless stars in the night sky are suns just like ours, possibly with their own planets, and perhaps even living creatures, then mankind is no longer the pinnacle of creation. The Catholic Church, very much in political power at the time, saw this way of thinking as a threat to its supremacy. As a result, Bruno was tried for heresy and burned at the stake. It seems that mankind was not quite ready to be dethroned from its status as the only reason the universe exists. Our quest for knowledge has had many detractors along the way, which should serve as a reminder of how privileged most of us are in modern times to have free speech, to have access to all the information we could ever want. We must value these freedoms and defend them from tyranny at all costs. But we haven't quite made it to modern day yet. There is more of the story left to tell. So let's see what astronomers did with the Copernican model next. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always,
I'm gonna play one more, and then I'm gonna get into it.
Professor Dave here. Let's talk about Kepler.
He knows a lot about the science stuff. Professor Dave explains.
The Copernican revolution, which placed the sun at the center of the solar system rather than the Earth, was a major event during the European Renaissance, a time when scientific thought truly began to flourish. In this climate, a figure like Danish astronomer Tycho Brahe was motivated to wield his status and wealth to build the most sophisticated instruments that had ever been built for the purpose of studying the heavens, and employ them to collect the best astronomical data yet collected at the time. Through meticulous observation of the planets and other objects, the Copernican model was corroborated much further, but the stage was set for further refinement of the model as well. Copernicus thought that the planets traveled in perfectly circular orbits around the sun, but this changed when Brahe's young assistant, Johannes Kepler, got his hands on this new data. He used it to determine that planets do not trace circles as they go around the sun. They trace ellipses. These shapes are discussed at great length in the algebra portion of my mathematics playlist. So if you want to know a lot about ellipses, click on this card now. But otherwise, it will be enough to simply understand that unlike a circle with its one center, an ellipse has two foci, and the sum of the distances from the foci to a particular point on the ellipse is a constant. When these foci get very close together, it starts to resemble a circle, since a circle is just an ellipse with foci that coincide. This is why the orbits of the planets seem circular, and why we operated under that assumption for so long. The brilliance of Kepler was to realize that the planets actually follow elliptical paths, with the sun acting as one focus of the ellipse. The point in a planet's orbit that is closest to the sun is called perihelion, and the point furthest away is called aphelion. The distances to these points are very close for most of the planets because the ellipses have very low eccentricity, but nevertheless, they are not circles. They are ellipses. This fact is the first of three laws known as Kepler's laws, which essentially marked the birth of celestial mechanics. The second of Kepler's laws says that the orbital speed of a planet will vary according to its distance from the sun. It slows down when further away and speeds up when closer in. A little more formally, it says that a planet will sweep out equal areas over equal time intervals. So if we take this area, A, of the ellipse involving a part of the orbit that is closer to the sun, and this other equal area, A, of the ellipse involving a part of the orbit that is further away from the sun, the distances traveled by the planet, either C to D or M to N, in order to sweep out these areas, are of different magnitudes. However, the planet moves faster when close and slower when far away, in a manner that results in precisely equivalent time intervals. And Kepler's third law states that the amount of time a planet takes to orbit the sun, or its period, is related to the length of the semi-major axis. That's this length here, or half the major axis, which is the longer axis of the ellipse. Specifically, p squared is proportional to a cubed when measured in years and astronomical units, and the precise relationship will depend on the mass of the planet. These laws are derived from observation, and when we use these laws to predict the positions of the planets at any future moment, we find that they are extremely precise, which is all that any good science can hope to do. These laws were used to calculate the relative distances of all the planets from the sun, and had other practical applications as well. But the impact of these laws was much deeper than the merely practical. These laws represented the first time that a handful of extremely simple mathematical formulas were able to describe and predict the motions of the heavens to the utmost precision. It was undeniable proof that the universe obeys mathematical principles that are decipherable by mankind, which is the basis of the revolution that produced modern scientific thought. We were no longer helpless victims of the natural world, tumbling in darkness. We ignited a spark that lit the candle, that shined a light, such that we began to understand our surroundings. Roughly simultaneous to Kepler, an Italian scientist, Galileo Galilei, was observing the same night sky, but focusing on entirely different observations. He used the best telescopes of the time to see that the moon had distinct terrestrial features, like mountains and craters, just like the Earth. This transformed the moon into a world unto itself, rather than just a mysterious glowing disk. He noticed the dark sunspots on the sun, which changed position over time, thereby deducing the rotation of the sun. He observed Jupiter's moons, and as they orbit Jupiter, this proved that not everything in the solar system orbits around the sun or the Earth, no matter which of the two you put at the center. He saw what we would later understand to be Saturn's rings. He observed the phases of Venus, demonstrating that it must be in orbit around the sun, just as the moon is in orbit around the Earth, the final nail in the coffin for the geocentric model. And he observed far more stars than were previously visible to the naked eye, indicating that the universe is much bigger than was thought at the time. Although he is often better remembered for being the father of the scientific method, as well as all of his contributions to classical mechanics, Galileo did as much as anyone else ever did to rewrite our perception of the cosmos. This earned him the same contentious status with the Catholic Church as Giordano Bruno. But Galileo was a little less stubborn, recanting his work under pressure, and he was sentenced only to house arrest, living the last of his years confined to his home. The year that Galileo died was the same year that Sir Isaac Newton was born, and his contributions to science were immeasurable. Beyond his laws of motion, he also provided the first accurate description of the gravitational force, which was then used in a stroke of genius to demonstrate that objects fall to the Earth for the same reason that the Earth goes around the sun. And he thereby demonstrated that all three of Kepler's laws were consequences of his own laws of motion and universal gravitation. All of this is described in detail in my classical physics series, so head there for more information if you're interested. Otherwise, let's continue our story. From Ptolemy to Newton, our picture of the solar system changed dramatically, leaving us with a perception about the universe that did not change much until the 20th century. We discovered 2 more planets beyond Saturn, as well as a host of other small objects, but heliocentrism and the elliptical paths of the planets around the sun were locked into place. With some historical perspective taken care of, let's move forward and take a closer look at each major object in the solar system so that we can become better acquainted with these beautiful worlds. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon.
Should I even do one more? I don't know if I should do one more. That was 4. Hold on, there's a commercial going on. I don't think y'all understand what I'm doing though, but it's okay.
Newton looked at the motion of the planets in their nearly circular orbits around the sun and understood that the centripetal. We've learned about what happened for the first billion years or so in the history of the universe, which leaves us with lots of stars and galaxies, and we are now equipped with the terminology needed to describe and categorize these stars. But we still haven't talked about all the other elements on the periodic table. We've only mentioned hydrogen and helium so far. So where did the rest come from? And what about all the planets and moons? How did those...
My bad, I got us too far up. He got the for those of y'all, he got a whole, what the hell? I don't know nothing about this. He has a whole series, right? But he walks everybody through the first stage all the way up until he started wanting to talk about all these other topics. And a lot of people, hold on, let me do it like this. It's easy if I do it like this.
little force causing this...
Let me go to show more. And then he has the full playlist. The full playlist will pull up. Let me change the quality. And where we end? We ended here, right? Nah, we're in this physics. I don't want no physics. Go back. There you go. Astronomy. Well, we end at 4. Yeah.
About the science stuff, Professor Dave explains.
We've learned about what happened for the first billion years or so in the history of the universe, which leaves us with lots of stars and galaxies, and we are now equipped with the terminology needed to describe and categorize these stars. But we still haven't talked about all the other elements on the periodic table. We've only mentioned hydrogen and helium so far. So where did the rest come from? And what about all the planets and moons? How did those get here? The answer to all of these questions will make sense once we learn more about what goes on inside a star, from the moment they are born to the time of their death. That's right, stars actually die, so to speak. And the type of death, along with what's left over, will be one of a variety of possibilities, depending entirely on the mass of the star. So let's go through the lifetime of a few different kinds of stars so that we are ready to understand the next 13 billion years of development in the universe. The life cycle of any star, from birth to death, and all the stages in between, will span millions or even billions of years. This is why stars don't seem to change at all, because a human lifetime is a snippet of a fraction of a blink of an eye to these behemoths. The path that will be followed by a particular star depends mainly on its mass, or how much gas collected and collapsed to form the star. because that material will serve as the star's fuel. As we may remember from physics and chemistry, when nuclei collide with enough energy so as to overcome the electromagnetic repulsion between them, the strong nuclear force takes over and they fuse, with a small fraction of their mass converting into huge amounts of pure energy, as dictated by E equals mc squared. Therefore, only by colliding nuclei together and fusing them in its ultra-hot core can a star release enough outward energy to counter the effects of gravity relentlessly crushing inward. This means that the amount of matter that forms the star determines the amount of fuel, and through a variety of other factors, the lifetime and eventual fate of the star. Given that mass is the key factor here, let's start with a low-mass star. This would range from the smallest that stars can be, meaning the smallest amount of material that can sufficiently trigger nuclear fusion so as to qualify as a star, which is about 13 Jupiter masses, to a star somewhere in the ballpark of our sun's mass. As we already know, any star will begin as a cloud of gas and dust, at least a few light years across. In the earliest era of star formation, this material was almost exclusively hydrogen and helium, as this was what remained after the brief 17 minutes of nucleosynthesis soon after the Big Bang. This matter collects due to gravity, pushing increasingly inward as it contracts, until things get so hot over a few million years that nuclear fusion eventually begins, establishing an equilibrium and generating a yellow or red main sequence star that glows with all the energy released from the collisions happening inside. These fusion reactions begin with two protons fusing, followed by subsequent beta decay to get a proton and a neutron, and we call this a deuteron, which is a nucleus of heavy hydrogen. Then deuterons are involved in reactions that make helium, which has two protons and two neutrons. Such a star will continue in this manner for billions of years, slowly fusing all of the hydrogen in its core into helium and maintaining a relatively steady size, temperature, and luminosity as it does so, until almost all of the hydrogen is gone. At this point, things really begin to change. The core of the star will shrink and get hotter, which makes the remaining hydrogen burn even faster, and all of that extra energy being generated will radiate outwards and push the outer layers away from the core. As the outer layers expand, they cool, and thus become more and more red, and the star climbs up the red giant branch until we have a red giant star. The star can maintain this new status for a little while longer, around 1 billion years, but after almost all the hydrogen is gone, the core gets even smaller and even hotter. At this stage, a phase called Helium Flash. Things are so hot that the star is able to fuse these heavier helium nuclei into larger nuclei, like carbon and then oxygen, through something called the triple alpha process. And this means that the star has a whole new source of fuel in all the helium it has been making for billions of years. The star begins pulsating as it runs through its final energy reserve, entering what we call the horizontal branch. And in this time, it becomes smaller, hotter, and bluer, until at last, much of the helium has been fused into larger nuclei. Once the core is predominantly carbon and oxygen, with just a shell of helium around it and a shell of hydrogen around that, the star has very little material left to burn, so the core will collapse and the star enters the asymptotic giant branch. This means it will grow rapidly and become a giant star again, until the last bursts of energy eject the outer layer, pushing it away from the core and back into the interstellar medium, leaving only a tiny, very hot, bare core behind, about the size of Earth. This will gradually cool as it has no more fuel to burn, not being hot enough to fuse carbon or oxygen nuclei, and it will contract further until we are left with a white dwarf star. The ejected shell is called a planetary nebula, which is misleading since it is not a planet and did not come from a planet, but the name originated from confusion upon its discovery, and it stuck. The material in a planetary nebula will then become available to join more gas particles to form yet another star.
Let's go help people customize and save with Liberty.
Find it quite interesting. When you ask a question, you can't get a direct answer. So then you gotta go with the science, you got the astronomers and let them break it down to you.
Now, for a high mass star, once much more massive than our sun, things are quite different. Their demise will not be so quiet. Big stars go out with a bang. Things start out normally with a gas cloud collecting under the influence of gravity. It is simply that this cloud will be much larger than those that form low mass stars, so it will contain much more mass. More mass means more gravity, which means the force pushing inward is much stronger and the star gets much hotter. A hotter temperature means faster fusion, which generates greater outward pressure to counteract the greater inward pull of gravity. This will result in a main sequence star that is hot, big, bright, and blue. This is where things start to go differently from low mass stars. Whereas low mass stars take billions of years to use up all their fuel, high mass stars are much hotter and burn their fuel much faster. That means they use up all the hydrogen in their cores in around just a fleeting 100 million years, or even 10 million if big enough. As the fuel starts running out, the core contracts and heats, producing more energy, so the star will swell up into a giant star, just like we saw for low mass stars. But while the core of a high mass star continues to compress, it gets much hotter than the core of a low mass star, and it becomes able to fuse helium nuclei to form carbon, and then oxygen, and then neon, and then silicon, each heavier nucleus being relegated to a smaller and smaller region of the core that is hot enough to fuse it. All the way at the center sits the heaviest element that can be fused within a star, iron. As this occurs in these different layers, each performing a particular type of fusion until no fuel remains, the star is left with the core of iron nuclei that are so stable that further fusion can release no more energy. At this point, gravity wins the fight, and the star collapses within a single second, the outer layers bouncing off the core and triggering an explosion, thus ejecting all of the heavy nuclei the star has created out into space. This awesome event, one of the most violent and energetic phenomena in the universe, is called a supernova. A supernova generates such an unbelievable burst of energy that in this brief moment, dozens of elements heavier than iron can also be synthesized. Nickel, copper, zinc, silver, gold. Any element with an atomic number greater than 26 is made either in a supernova or a rare event like the collision of two neutron stars or a neutron star and a black hole, which are objects we will discuss in a moment. That's why these heavy elements are so rare compared to elements like carbon and oxygen, because stars can't synthesize them the way they can synthesize all the elements up to iron throughout their long lives. Nature only makes these rare elements during the death of a high mass star or in certain exotic collision events. Supernovae are also so bright that they are brighter than the entire galaxy they belong to when viewed through telescopes. And if in our own galaxy, they can even be visible with the naked eye, like the one that generated the famous Crab Nebula, which was recorded by a variety of civilizations in 1054. Now, a supernova does not leave behind a white dwarf. Lower mass stars that begin with less than about 8 solar masses leave behind white dwarfs, because once reduced to its lighter Earth-sized core, there is not enough gravity to overcome electron degeneracy pressure. In other words, a white dwarf will become kind of like one gigantic metallic solid, with the electron clouds around the nuclei pushing against each other and preventing further collapse. Even still, this object is very dense, with 1 teaspoon weighing around 15 tons. So below around 1.4 solar masses, the maximum mass of a white dwarf, which is also known as the Chandrasekhar limit, this is the fate of the core of a star. But for a high mass star, where upon its death, the core of the star is above the Chandrasekhar limit, which means it is massive enough for a supernova to occur, one of 2 things will be left behind. If the core is between around 1.4 and 3 solar masses, having been generated by a star that was originally somewhere in the ballpark of 10 to 40 solar masses, the core will not be able to support itself against gravity, and it will collapse with such tremendous force that all the electrons get squeezed into protons such that they combine to form neutrons. And the shock wave from this event is what triggers the supernova. The object that remains is a ball of neutrons bunched up together like one huge atomic nucleus the size of New York City, containing all of the mass originally within the core of the star. A teaspoon of a neutron star would weigh a whopping 10 million tons. But even more miraculously, if the core of the star is above around 3 solar masses, even the outward pressure of neutrons pressing right up against each other, or neutron degeneracy pressure, is not enough to stop the immense gravity, and the neutrons will be crushed together as the remaining mass collapses into a single point of infinite density. The entire mass of the star's core contained within 0 volume. This object is called a black hole. The outer layers of the star that have been ejected, full of heavy nuclei fused during the lifetime of the star, and the additional, even heavier ones formed during the supernova, will leave behind a colorful nebula. But the singularity that is left behind is anything but colorful. A black hole, given its infinite density, warps space-time so much that not even light can escape. Whatever a black hole might look like, if that can even mean anything, we will probably never find out, because it is impossible for photons to leave it and reach our eyes, which is how we see things. As incredible as this may sound, this is how nature works, and black holes do indeed exist all over the universe as the remnants of huge dead stars. Black holes are so fascinating that they will require a whole chapter unto themselves, which we will get to in a moment. For now, let's review what we just learned about the lifetime of a star. When a star forms from a gas cloud of some mass, which is almost always between 1/10 of a solar mass and around 30 solar masses, a star is produced somewhere along the main sequence. As the fuel in the core begins to run out, it contracts, which raises the pressure around the core and pushes the outer layers outward, where they will then cool, producing a red giant. So all stars will have a red giant phase when their fuel is almost gone, regardless of their mass. Then finally, when the star can no longer perform sufficient nuclear fusion so as to counter the effects of gravity, the star will collapse, leaving a white dwarf if it is of low mass, a neutron star if it is of intermediate mass, and a black hole if it is of especially high mass. As we mentioned, black holes are among the most fascinating objects in the universe, and they are a popular area of study amongst astronomers and theoretical physicists alike, because there is so much that we still don't understand about these strange creatures. Let's move forward and learn a little more about black holes. Thanks for watching, guys. Subscribe to my channel.
I don't even want to get into the whole black hole thing. I don't. I want to skip all of that.
DiGiorno has 7 delicious crusts.
Come on, man. All these dang on egg commercials.
Professor Dave here. Let's look at the Earth.
He knows a lot about the science stuff. Professor Dave explains.
The inner planets of the solar system are terrestrial planets, which means that they are rocky worlds. And the third rock from the sun is Earth, our home planet. Although it seems that we are extremely close to achieving manned missions to other planets, at the time of the writing of this series, every human being that has ever existed was born on Earth, lived on Earth, and died on Earth, never to set foot on any other planet. The dawning of the space age and the potential for future colonization efforts will be discussed later in this series. For now, let's just go over what we know regarding the formation of the Earth, as well as its large moons.
It's finna get
Our
interesting.
first encounter with such an object, as Mercury and Venus do not have any natural satellites.
Go on, explain it to us.
When we talked about the formation of the solar system, we envisioned a protoplanetary disk full of heavy elements ejected into the interstellar medium during the death of one or more stars. We also saw how the matter in this disk collected into pebble-sized and then boulder-sized chunks, and eventually into large planetesimals a few miles across, all due to gravity. Over hundreds of thousands of years, these combined further to form rocky objects so large that their shapes were crushed into spherical form by the immense gravitational field that had been generated. One of these rocky objects was the early Earth, which was in a largely molten state due to all the heat generated by these incredible collisions.
Heat, huh?
Once most of the matter within Earth's orbital radius had been collected, collisions became more rare, giving the Earth the opportunity to cool down and form a layer of crust.
Cooling
with the
phase.
last round of major collisions producing craters and releasing huge quantities of gas trapped in the rock. This gas remained gravitationally bound to the planet, along with other gas ejected during volcanic eruptions, thus generating the early atmosphere. Comets eventually delivered more of the atmosphere as well as lots of water during the late heavy bombardment we mentioned before, but we will talk about comets later in the series. After continued cooling, water vapor condensed to form all the oceans, and thus the primitive Earth was born. We've already discussed how the size of the Earth was...
Whoa. Did he just call the Earth primitive? Did he just call... Did this man just say that the Earth was primitive? The primitive Earth has formed. Did he just say that? I kind of heard that somewhere else before. So I just wanted to see if an astronomer would say that. Oh, y'all didn't know that. Okay.
We've already discussed how the size of the Earth was determined, which is around 13,000 kilometers in diameter. The composition of the Earth is obviously much better understood than any other object in the solar system, since we are living on it and have perpetual direct access to it. The core of the Earth is made mainly of iron, with some nickel, and is divided into a solid inner core and a liquid outer core. This core is surrounded by a rocky mantle comprised largely of different combinations of silicon, aluminum, and oxygen, which we call silicates, although there are lots of other metals and minerals as well. And all the way at the surface is the crust, a thin layer of rock that we walk around on every day. We will notice that just like with other planets, density determines the distribution of matter, with the heaviest elements found at the center, mainly iron, which is 8 grams per cubic centimeter, and lighter compounds distributed upwards towards the crust, like most rocks, which are around 3 grams per cubic centimeter. Liquid water, being 1 gram per cubic centimeter, sits upon the surface, filling in the nooks and crannies. Lastly, extremely light gases float above the surface in our atmosphere, warming the planet and shielding us from UV radiation. These gases include nitrogen, comprising 78% of the atmosphere, oxygen, which is most of the rest, and then some argon and just a little bit of water vapor, carbon dioxide, neon, ozone, methane, and a few other things. The very lightest of them, hydrogen and helium, are so light that they can escape Earth entirely, floating off into space. So we can see that density really is the determining factor in terms of the distribution of substances. This phenomenon regarding the separation of materials by density is called differentiation, and it happens in large bodies of molten material, like newly formed planets, just the way that substances separate by density in a centrifuge. Going back to the interior, as we said, the outer core is liquid, with the mantle above also capable of very gradual flow. And for this reason, sections of the crust drift over time, which is called continental drift. It was through collisions of these tectonic plates over millions of years that has produced the major mountain ranges we see today. The circulation happening in this molten core, when combined with the rotation of the Earth, allows for the alignment of unpaired electrons, which generates an incredible magnetic field. This magnetic field shields the Earth from cosmic rays, deflecting high-energy charged particles to the poles, which then collide with atmospheric particles to form the dazzling aurora borealis, also known as the Northern Lights.
There are
He going in. I ain't gonna lie to you. He going in.
So those are the basics regarding the Earth. We could talk for days and days about its composition, but that discussion belongs to the field of geology. So we will have to pick things back up in the upcoming geology series. To get back to astronomy, we have to deal with Earth's moon. Where did this come from? First, let's make the distinction between a planet and a moon. A planet orbits a star, while a moon orbits a planet, meaning it is a natural satellite of a planet. Earth has just one moon, visible as the most prominent feature of the night sky. The evidence is very clear in suggesting that the moon is the result of a collision between two huge planetesimals in the early stages of Earth's formation. One of these was to become the Earth, and the other must have been a Mars-sized object. And when these two objects crashed into one another, enormous amounts of rock were splashed up into space. This debris, gravitationally bound to the Earth, eventually collected to become the moon, just the way all the planets initially formed. This model also explains the composition of the moon, rich in silicates and poor in iron, since only Earth's mantle was blasted apart from the collision. It also explains the tilt in Earth's rotational axis from the impact, and so many other features about this two-body system. The moon was able to cool very quickly upon forming due to its small size, resulting in a rocky crust covered with craters, as well as dark patches called maria. With such a small size and cool interior, there is no mechanism by which the moon's features can change, so it has looked pretty much like it does now since very soon after its formation. There is no atmosphere, as any gas can easily escape the moon's gravity, and therefore no wind, which is why the footprints made by the men who have been on the moon will likely remain intact for millions of years. The moon orbits the Earth once every 27 days or so, and its rotational period is exactly the same as its orbital period, meaning it rotates on its own axis once in the same time that it takes to orbit once. This is called synchronous rotation, and it is the reason that we are always looking at the same side of the moon. This phenomenon is a result of tidal forces between the Earth and the moon, and this gravitational force is also responsible for the tides on Earth. The moon tugs very slightly on the Earth, and all the water in the oceans, being liquid, will actually bulge out slightly towards the moon, causing high tide in these areas and low tide in these. The moon will tug in this manner constantly, but as the Earth rotates, the locations where the bulges can be found will change, and thus in any particular coastal location, the tides come in and out over time. There are solar tides as well, although they are much less significant than lunar tides. In this way, the moon and the sun are the only two objects in the universe that have significant gravitational influence on the Earth. As it happens, we believe that the tides may have been a crucial component in the development of early life, so it's possible that without the moon, life on Earth would not exist. Speaking of life on Earth, we've now really tied everything together, from the birth of the universe to the formation of our galaxy, and then our solar system, and even our planet, all the way until conditions were such that life could begin. Phytoplankton and eventually plants began to generate all the oxygen we have today by photosynthesis, setting the stage for complex animal life. Over millions of years, that life produced humans, who were then free to look up at the sky and realize that we are on a spinning rock close to a star, which is part of the Milky Way galaxy, which is sitting in the Virgo supercluster among billions of other galaxies in the observable universe. This might make you feel very small, but in fact, it should make you feel powerful. The fact that we can decipher all of these details about the universe may be an indication of how much more we will soon learn, and perhaps all the places we will someday visit. Speaking of visiting distant places, the other planet that humans will set foot on first is definitely going to be Mars. So let's learn about that planet next.
All right, man. I just wanted to get into that a little bit and kind of share with y'all what astronomers are actually saying about how the Earth formed and all of this stuff, but to walk you through the actual process so that you can understand for yourself and you won't catch a biased opinion about something or an emotional response towards something. Especially when you start analyzing and looking at teachings from different cultures regarding certain aspects of the cosmos and how things came to be under their interpretation and understanding, because they didn't have certain tools or whatnot to deal with certain things. However, there was some interesting points in how the Earth came to be. You know, if you if you were to create some type of story, if you could take if you were to, based on what you learned, if you took a type of story, you created a story that would fit a better explanation than what Buddy just did right there, man, children will love it. This is why I said, if you're talking to, certain people who have certain things going on with them, like you got to meet people where they are. It is what it is, but I don't even want to get no far into it than what we are with it. He said, yes, sir, they did. One reason why I love astronomy. Want to hear what ancient civilizations recorded about the night and sky? I could see it. Just amazement. Yeah, it's true. But I just wanted to come and drop them seeds on y'all, man. Y'all can go over there and get more familiar with the Buddy channel, and if you want to. But I'm leading y'all to all the experts. I ain't no middleman. No middleman. You know what I'm saying? I'm gonna take you to the experts and then let y'all do your thing with that, and kind of get it in how you want to get it in and how you see fit in that regard. So I appreciate everybody for tuning in. I just wanted to throw that out there. Y'all enjoy the rest of y'all evening, man, and y'all festivities, whatever y'all getting into.